Greetings, fellow mathematicians. In this video, we're going to apply the integral test to an infinite series in two ways. First, we'll do it in an easy way, and then a second way will be much harder. So first, let's translate our infinite series into an improper integral. You can do that very quickly. Replace n with x, and we get this improper integral of 1 over x squared plus 1 from 1 to infinity. Your function of x is 1 over x squared plus 1, and always make sure that you check the conditions. So first, this function is continuous on the interval from 1 to infinity. There's no discontinuities, there's no division by 0, so this function is continuous. Second condition, this function is positive. Notice in the denominator you have x squared, but it's x squared plus a number. That's always positive. So we don't have to worry about any division by a negative number or anything, since the numerator is just positive 1. So it's definitely positive. And then the third condition that you need is that this is a decreasing function. And if you take a look here, we only have x's in the denominator. And if you make your denominator bigger, in other words, if you increase the value of x, like n going from 1, 2, 3, so on and so on, when your denominator becomes bigger, the fraction gets smaller. So that's enough for us to conclude here. Since the denominator gets bigger, we would basically say that fraction gets smaller. So this function is decreasing. All right, great. All three of the conditions are met for the integral test, which means we can now apply the integral test. So we're going to determine if this improper integral converges or diverges. The easy way that we're going to do this you can just apply the comparison test for improper integrals. And that was probably a few sections ago, but not too far ago, in your Calc 2 course. And here, this will be very easy. This looks like a convergent p-integral. We can make a bigger function by making the denominator smaller. So this is going to be less than the improper integral from 1 to infinity. We're going to make the denominator smaller by getting rid of the plus 1. So we get now 1 over x squared. And that is a convergent p-integral. Since the value for p is 2, which is greater than 1. So what we conclude is this improper integral is convergent. And if we were to write that out, since the integral from 1 to infinity of 1 over x squared, since this is convergent, and again we determined it was convergent by applying the comparison test to a convergent p-integral. Well, remember, for the integral test, the improper integral and the infinite series do the same thing. So since our improper integral is convergent, the infinite series from 1 to infinity, but now the term is 1 over n squared plus 1. That infinite series is convergent. So there we go. The easy way here is to apply the comparison test for improper integrals. We're going to see the way to directly evaluate this right now requires a lot more work. Next up, we're going to do this the hard way through direct evaluation. Now it's actually not that hard because 1 over x squared plus 1 has a basic antiderivative, which is inverse tangent. This problem is probably going to be hard through direct evaluation because you're probably not as familiar with inverse trig functions as you might like to be. But we'll go through it so that way you can develop those ideas. We have an improper integral here of the first type. We have an infinity in the integral sign, so let's replace the infinity with t, and then we'll take a limit as t approaches infinity. So let's set this up properly. Limit as t approaches infinity. And then our integral goes from 1 to t. Of 1 over x squared plus 1. We turn our attention to evaluating the integral. So our integral goes from 1 to t. We immediately have an antiderivative. We don't need any integration methods. The antiderivative is just inverse tangent of x. And we're going to evaluate that now at x equals 1 and x equals t. So we're going to plug in and subtract with the fundamental theorem of calculus. We get inverse tangent of t minus inverse tangent of 1. And as a calculus student, you should be comfortable with some special values for trig and inverse trig functions. You might recall that tangent of pi over 4 equals 1. And from our basic understanding of inverse functions, that's then going to imply that tangent inverse, or inverse tangent, of 1 should be pi over 4. So that value there, inverse tangent of 1, that equals pi over 4. So we get the value for our integral, which is inverse tangent of t minus pi over 4. All right, we can now plug the value for the integral right up here. And what we have is a limit as t approaches infinity of inverse tangent of t minus pi over 4. And this is where you need to be comfortable with some basic facts about inverse tangent. Here we just really need the graph, and this pops up enough through the calculus sequence that you'll want to be familiar with it. Notice as we go very far to the right, the graph of inverse tangent has two horizontal asymptotes. As you go very far to the right, inverse tangent is going to approach the asymptote y equals pi over 2. So when we take a limit of this term, as now t approaches infinity, here in the graph we have x, but as x approaches infinity, tangent inverse of x approaches pi over 2. This should also approach pi over 2 as t approaches infinity. All right, and if we take a look at that, looks like we get a finite value here. We get that this limit is going to be pi over 2 minus pi over 4. And if you work that out, since the limit here works out to be a finite number, the limit here exists. So our improper integral is convergent through direct evaluation. Now we just need to make this precise with the integral test. And it's always good to write that. So since we've now determined that the improper integral from 1 to infinity of 1 over x squared plus 1 is convergent, remember, with the integral test, your infinite series does the same thing as the improper integral. So this infinite series is also convergent. And that completes this problem going through the improper integral with direct evaluation. The first way, using the comparison test, is much shorter, but the comparison test might not always be obvious to apply. Just like here, doing this with direct evaluation, this only usually works if you can actually find an antiderivative. So we applied the integral test here kind of in two ways, using the comparison test and then direct evaluation for the improper integral. Hope you enjoyed the video. If you did, support the channel, like and subscribe.